TierTrain, and we'll look at why and how we can place data across different tiers for DNN training workloads. So we'll be going over the motivation for why we want to do this and some necessary background, and we'll be looking at. Is it working now? Yeah, and we'll be looking at the core of the work, which is TierTrain, and some results. So, why is using DRAM not enough for DNN training applications? Well, on a general note, in most data centers, DRAM accounts for about 50% of the overall cost. So it's getting more and more expensive. And we also noticed that in a report from VMware, it costs around 90% of the overall cost, which is around 50% of the total TCO. So we can see that the cost of DRAM keeps going up, and as your workloads become bigger and bigger, this issue is only going to get more worse. So why do we want to use this for deep learning models? Is because as the model size goes up, we are going to access a lot more weight parameters, and then the memory requirements also shoot up. So we will require more DRAM to run these models, and soon computer is no longer going to be an issue. It's memory that's going to become an issue, and so we have this popular memory wall problem that we come across, and we are looking at memory tiering as a solution to address this memory wall problem. So this is just some background on memory tiering. So in a typical memory tiering system, we have multiple tiers of memory, meaning on different levels, we will have different memory technologies which have very different characteristics. So for example, in your typical system, we have a cache which has a very low capacity, but it has a very high bandwidth, and the latency to it is very small. So similar to the cache, we also have something called high bandwidth memory, which is very prevalent on GPUs. And so these are hop memory tiers, meaning that we would want to place data that is being accessed very frequently on these tiers. And on the other end, we have cold memory tiers, something like CXL-attached memory or Intel Optane, which supports a very large capacity, but then the latency is very high and the bandwidth is very low. So we would just use this as a capacity tier where we would want to place data that's infrequently accessed. And coming to the key observation that we have made, which we'll exploit later on, is that, so on the right, we have the address space which shows the memory access pattern when we run a DNN training workload. So what happens when the forward pass runs is that, so every dot in this particular image refers to a single page being accessed. So during the forward pass of the first epoch, of a single epoch, what happens is a bunch of pages get accessed in this fashion. And during a backward pass, what happens is these pages get accessed again. So basically, a lot of tensors are being produced in your forward pass, which are again being accessed in the backward pass. And the same thing happens in the second epoch too. So there are tensors. So DNN has multiple layers, and each of these layers, they produce a lot of tensors. So these are referred to as safe tensors, which are basically intermediate tensors, which is written to in the forward pass, and it's again being read in the backward pass. So we notice that there are some tensors that are being produced by every layer in your forward pass, and it's going to get accessed in the backward pass, but it's going to happen in the reverse order because gradient descent runs in the reverse order. So for example, a tensor that's being produced in the first layer in the beginning of the forward pass, in the beginning of the epoch, gets accessed only again during the end of the first epoch because the backward pass of the first layer runs towards the end. So there is a lot of idle time, and idle time basically refers to the period of time for which these tensors don't get accessed. So the idle time for, say, these tensors corresponding to the first layer is very huge, which means it does not get access for a long time. Whereas if we look at the final layer of our network, it gets accessed immediately after, leaving it zero idle time. And the same pattern is observed across different epochs. So TierTrain is going to try and exploit this fact because there's a lot of time over here for which is not being accessed, so we don't have to store all of these tensors in some fast, expensive memory like DRAM. Instead, we can offload it to a different medium. So this is what TierTrain roughly does. So in frameworks like PyTorch, we basically have hooks which can provide us information on all of these tensors, including their size, their address, and the timing information of all of these layers. So we get this information and then we pass it to TierTrain, which is basically a daemon running in the background. And then TierTrain knows when a layer is going to finish. So once a layer is going to finish in the forward pass, what happens is whatever saved tensors has been produced can now be migrated to a different memory tier, which is not as expensive. And the amount of data it wants to migrate depends on how much memory bandwidth is available on the system and other factors. So this basically is being migrated, and again we want this data to be prefetched back in time before the same layer in the backward pass accesses those tensors again. So it's going to decide whether to prefetch this tensor or not, depending on whether it has been migrated in the first place. And if it has to prefetch, it's going to prefetch how much ever data it evicted back to your fast tier, so that we don't have to face the consequences of the workload accessing this data from the cold tier, which will lead to a lot of performance loss. So we have a simple queuing system which takes care of when and how much data to evict during the forward pass. So we basically get the duration of a layer, the size of all of these tensors from the hooks, and then we trigger eviction right after a particular layer gets evicted during the forward pass. And like I said, the size of this eviction depends on how much memory bandwidth we have available, and what is the idle time for these tensors. So for example, if we look at layer number 3, then it's going to be accessed immediately after. So we decide not to evict these tensors at all. It's going to be present in DRAM at all times. And all of these tensors get accessed in the reverse order during the backward pass. So the prefetch has to be triggered at the right amount of time so that it gets prefetched before these tensors are accessed again. So we don't want to prefetch these tensors too early, because if we prefetch them too early, then it's going to occupy more of the fast memory for no reason. And we don't want them to prefetch them too late either, because that would lead to a performance loss. So we have these equations running in the background which determine when exactly we want to trigger a prefetch. And now we can look at some results of TierTrain. So initially we did an evaluation on real CXL-attached memory, and so these are the results we have observed. We have around 2 terabytes of DRAM on the system and about 256 GB of CXL, and we have tested TierTrain across different variations of ResNet on CXL, and so we can notice that on an average the DRAM reduction is about 48 to 59%, with the baseline being execution in pure DRAM. So the highlighted line here is the pure DRAM number, and then there's very minimal performance impact because most of the data is being prefetched back in time. So there's about 1 to 5% performance impact. And we have also done the same evaluation on a system that has both DRAM and Optane. So there is 768 GB of DRAM and 4.5 terabytes of Optane being supported on the system. And we compare this against other tiering tools such as MEM-TRD and HBM. And the baseline here is again pure DRAM execution. And so compared to all of these methods, there is again an average DRAM reduction of 59 to 83%. There's a peak DRAM reduction of 25 to 74%. And this has been tested across various benchmarks like your transformer models and a lot of graph neural networks and a lot of CNNs like ResNets. And we also want to see what would happen if the available DRAM on a system is not enough to support the overall footprint of the application. So for this example, we have chosen ResNet 152, whose footprint is 150 GB, and we only have 60 GB of DRAM supported on the system, and about 1.1 terabytes of Optane. And then we compare this against Autonoma, which is a tiering policy that is supported by Linux, and MEM-TD, and our baseline is again pure DRAM. And we notice that, so what happens in this case is, once the DRAM runs out, most of the data is going to spill out into Optane in the baseline. So that's going to lead to a lot of performance degradation, takes around 2000 seconds. And MEM-TD and Autonoma and TierTrain in the background, they try to reshuffle this data across different tiers. And we notice that TierTrain outperforms MEM-TD, HBM, and Autonoma by 35, 37, and 84% respectively. And one reason for this is that all of these tools, they are not tailored for DNNs, DNN training's memory access patterns. So it is a very, very reactive way to tiering data, as in it first detects that some data is being accessed and it realizes that it's hot, and then it moves it to a hot tier. But by the time the data might have already been accessed, so it might be too late. So TierTrain does it in a proactive fashion where it receives all of this data from the hooks, and it knows exactly when to prefetch and evict all these tensors. So in conclusion, all the existing solutions, they are inaccurate and they are slow in the sense that they might not be able to prefetch all of this data in time once the data has been detected to be hot. And TierTrain addresses these challenges by understanding the DNN training workload pattern. So basically we have the first epoch, which is sort of a profile epoch where it gets all of this information, and then it starts tiering data from the second epoch onwards. And yes, it does this in a proactive fashion where it doesn't have to wait for the data to be accessed. It just prefetches all the tensors in advance. Thank you.
We have time for some questions.
Hello, I'm Singhan Nam from Seoul National University, and actually your work looks awesome because from the performance and the RAM reduction. But in real world, as far as I know, most of the training are done using GPU or accelerators. Then, could you apply the same tactic for GPU and accelerator-based training, or could there be some peculiarities that prevent them from being easily applied?
So the technique prescribed here is agnostic. It can run on GPUs as well as any accelerators that support data movement. So here we did it on CPUs because, so basically the implementation alone is CPU specific. It can very well be done on GPUs. You just have to change the implementation and use the according calls for performing the data migration, but it can be performed on GPUs, yes.
Thank you for the great talk, Tomoharu Gawa, University of Tokyo. And my question is related to the previous question. So if you use a GPU, is the boundaries between the slow memory and the fast memory sufficient? So, if the bus between the slow and high memory is slow, it is we cannot prefetch enough data.
So in this case, TierTrain runs as a daemon. So all the migration is being done in the background while your DNN training application runs. So if I'm using a GPU, for example, all the transfers will have to happen across the PCI bus. Say if I'm trying to transfer it between CPU memory and GPU memory. So we'll just have to ensure that the prefetch is triggered at such a point in time that we are able to migrate the data in time to the GPU memory so that you won't have any accesses going across the PCI bus. And TierTrain also makes sure, for example, let's say you have a lot of data to transfer in very little time because sometimes the idle time of these tensors is very small, especially for layers towards TN. So TierTrain automatically calculates how much data can you migrate given that the idle time is only so much. So sometimes it chooses not to migrate the entire tensor and it only migrates a partial tensor.
Martin Mas, Google DeepMind. Really nice talk. So an alternative to keeping the data in memory is to rematerialize or recompute tensors. Have you looked at how your technique interacts with those approaches?
Could you come again? Which ones?
So instead of keeping the forward, like all the data from the forward pass in memory, you can drop some of it and then rematerialize it during the backwards pass. How does it interact with your technique?
We could recompute it, yes. So if we want to recompute, then there would be no memory tiering to perform because these sensors won't be present in memory. But then the memory requirements would be, if we recompute it, yes, the memory requirements would come down. That is not something we have looked at because the training by itself takes a lot of time. So in order to recompute it, the training time would be very high. So that's not something we have looked at yet.
Thanks.
We have time for another question if someone would like to ask one. Yes.
Hello, Jeremy Singer, University of Glasgow. I think your technique is very nice for repeated traversals of regions of memory. How complex can those traversal patterns be? The one you showed us was just kind of all the way down and all the way up. I'm thinking of maybe more complex traversals that kind of went over perhaps dynamic data structures that are very large or something like that. Would your technique be able to do prefetching for those kinds of things as well?
Right now, the technique is pretty tailored for the memory access patterns that we have observed. But if the daemon is fed with the right data, as in, say, if these iterations are occurring multiple times, and in the first iteration, the daemon knows, just gets a sample data as to when it has to prefetch and when it has to evict, then it is going to, use that same data to perform the evictions and the prefetches in the upcoming iterations. Coming to this pattern across a lot of models, we have observed the same pattern at least for DNN training applications because this is fundamental to gradient descent. But in case of more complex models where the network itself might change structure during training, I'm not sure if that happens. But if that happens, yes, this will slightly change. But what will matter more is the data that's being communicated between the DNN training workload and the daemon. So as long as that data is being fed in the format we expect it to be fed, then this would still work.
All right. Thank you.
Thank you very much.
Thank the speaker.